So EM wave is just one example of the all different kind of waves. So they definitely have their own speed when they are propagating in the space. So the speed of the EM wave is the so-called speed of light. And this value is a constant no matter which EM wave you're talking about. So this is a very intrinsic property for the EM wave. And this is also the highest, the fastest velocity a particle can reach. No one can even moving faster than this one. So this one will be a very important assumption for the special relativity, which is the chapter we skip. And for sure it is a wave, so they also have the Doppler effect. But now because of this unique upper bound speed, or I should say the unique speed for all the EM wave, then the Doppler effect looks slightly different. This u is not the velocity of the source or the velocity of the observers. Instead, it is the relative motion between the observer and the source. And this formula applies to all the electromagnetic waves, and they have distribution of the frequency. So therefore, we study the so-called spectrums, the EM wave spectrums. So from the low frequency to the high frequency, so from the radio wave to the gamma ray, we can see that the distribution of the EM wave. But you can also try to understand the spectrum in terms of wavelengths of that. So how did you determine the wavelengths of the radio wave or gamma ray if you know the frequency? Here is the relation which is true for all the wave is the velocity of the wave equal to the multiplication of the frequency multiplied by the wavelengths. So therefore, the higher the frequency, the shorter the wavelengths. So therefore, radio wave has the longest wavelengths. And because that the EM wave is composed of the electric field and magnetic field, so they carry the energy because there will be the energy stored in the electric field and in the magnetic field. So this is the energy carried by the EM wave. But in the chapter 30, when we try to quantize the EM wave in terms of photon, we know that this energy carried by a EM wave can be related and described by the frequency multiplied by h. And because EM wave is produced due to the oscillation of the electric field and B field, and we also learned that if you change the electric field, you produce a B field. If you change the B field, you produce the electric field. So they are not independent from each other. So the relation between the electric field and magnetic field is this: E equal to c times b, and c is the speed of light. And the intensity and the momentum carried by the wave basically just follow what we have learned before. But when you try to study the polarization there, then the intensity is a very important concept. So what is the polarization? It is determined due to the direction of the electric field, not due to the B field, due to the electric field. And the concept of polarization were very useful in the future when you went to the laboratory in the chemistry or in the biology laboratory. So let's assume that originally your light has no polarization, so it is unpolarized. And now you have an instrument called the polarizers, which is basically a filters. So what will happen is that they will only allow certain specific direction of polarization of wave to passing through. So in that case, if you know the direction, the axis of the polarizers, and originally it is unpolarized, then the intensity after passing through the polarizer will become half of original value. And the explanation is because all the unpolarized beam can be decomposed in terms of the component which is parallel and vertical to the direction of polarizations. So which means only the direction which is parallel to the polarizers are allowed to pass. That's the reason the magnet become 1/2. But this kind of discussion can be generalized to that is even originally you are polarized, but if your direction of polarization has an angle theta compared with the polarizers, then the intensity after that follow this relation, and you will see that this is just a special case of that. Now let's move on to the chapter 26. So this one will mainly focus on the classical optics. So we first define a quantity called the rays. What is the rays? It is the direction of the wave propagation. So based on that, we can study the law of the reflection. Is that if this is the direction of incident ray, and this is the normal line, and this is the direction of the reflected ray, the angle between the incident ray and the normal line should be the same as the direction between the normal line and the reflected rays. This is the law of the reflections. And this law of the reflection applies to all the mirrors. So let's study that for the plane mirror. Because of the reflection law, the image will be formed behind the mirror. But this image will be left and right reversed. The distance from the image will be the same distance from the object to the mirror, and the size will be the same as the object. So this reason we use that to see our image. But the mirror could be spherical one, so it could be the concave, which curve inward, or convex, curve outward. So now it is still a mirror, so the law of the reflection is still true, but the relation will be different. But now I have to help you to refresh what is f. F is the focal length. So focal length is the distance from the focal point to the center of the spherical mirror. So how do we find out the focal point? If you have the parallel ray incident on the spherical mirror, the reflected ray will passing through the focal point. This is how we define it. And the focal point is different from the center of the circle, the spherical mirror. R is the radius of the circle. Okay, so they are different kind of concept. And when we say the image is formed real or imaginary, it depends on that. If it is real, then it is the real light intersect and the center at that point, and this is the real image. If it is the virtual line, which is a dashed line, center at that point, it is a virtual image. And for all the mirrors, they follow these mirror equations. So the distance from the object and the distance of the image can be related to the focal length together. And then we define the magnification. So in the our lecture of the chapter 26, I defined that originally the definition is the size of the image divided by the size of the object. But now it can be rewritten in terms of this. So these are very two important equations. So now we only focus about the light interacting with the mirror. So the light cannot enter into the mirror. So this is why it is important for the reflections. But now let's assume that the light can enter in some material. So they are now reflected. So this is a so-called refractions. So what happens, why the refraction happens is because the direction of the light is changed. And why the direction of the light is changed is due to the speed of light is different at a different material. So the speed of a light is a constant in one material, but it will be changed if they move to, for example, from the air to the gas, from the glass. So the speed of light in that material is described by this. So this is speed of light in a vacuum in the air, divided by the so-called index of the refractions in that medium. So the velocity definitely will become smaller. Or the index of the refraction is bigger than 1. So the more dense the material, the slower the velocity of the light in that material. So based on that, the concept of the refraction can be described by the Snell's laws. So N1 is the material for example, in the air and enter into the glass. So N1 is the index of refraction in the air, and N2 is the index of refraction for the glass. It depends on which one is the incoming one and one is the refracted one. And the angle is still determined in terms of the compared with the normal lines. So apparently, the higher the index of refractions, they will be bended more toward to the normal line. Okay? And if you are entering to a lower index of refraction, it will be bended away from the normal line. So depending on how fast, how big the change of velocity, it will determine whether it is bended toward and away, and also it will be bended more toward to a normal line or less. So it depends on index of refractions. But you can also think in terms of the speed of light. So you have to make sure that you can connect this one to the pictures I just described to you, the speed of light in that material. And now there's a very special condition is that instead of refractions, all the light still will follow the concept of the reflections. So this is so-called the totally reflections, which simply just mean that the angles, the reflected angles, respect this critical angle here. And this critical angle is related to the index of refraction for the two different materials. And for another very special angle, which is different from the totally internal reflection, is the Brewster angle. This one, they will have both the reflected and the refracted light. But now this reflected light is totally polarized, and this angle is also described in terms of n1 divided by n1. So the lens is the instrument to describe this kind of refractions, because they are entering from one material to the other one, so the light will be bended and form the image. So therefore, not for the mirror, this is for the lens. They also have the thin lens equations. And you will say, oh, it looks very similar to the one we have. Yes, you're right. And the way how you calculate magnification is the same, but this is for the lens, so don't forget about that. And now let's go to the chapter 28. So now this can consider, this is just a continuation of the chapter 26, is that now if you have two light sources and they produce light, they will interfere with each other, like the interference we studied in the chapter 14. So definitely you will produce the constructive and destructive interference. So we try to study is that in the Young's double slit experiment, you will see a very interesting pattern, which is the light and the dark fringe due to this interference. And what is the result for that? So now for the bright fringe, this is the distance between the two slits, and this is the angle to that specific fringe. And m is the particular number we give for the maxima, the central one, or the first fringe, the second fringe. So m is that value, and lambda is a wavelength. And you see there, it is just one single wavelength. It is due to the source we produce is that monochromatic source, because they all have the same frequency. So this is the assumption when we try to do the double slit experiment. So this is the wavelength of the light produced from the source. And now for the dark fringe, the relation is this one. So you can see now, based on this, it will be a distribution of the interference pattern here. Now in the chapter 30, we try to quantize the EM wave as a particles, because in order to explain the concept of the black body radiation, now the energy carried by the EM wave becomes h times f. H is a Planck's constant. And now you can also rewrite it in terms of the wavelengths using the relation C equal to F multiplied by the lambda. And now we use this quantization of the light to study the photoelectric effect, such that the light is not a wave anymore, it is a particles. And the particle of the EM wave is the photon. So the photon will interact with the electron and excite the electrons, and they will leave the surface of the matter. There's a minimum energy required, which is work functions. So which means there's a minimum frequency. It is not any arbitrary light can excite the electrons. So this is a very important step, is that the wave property of the light cannot be used to understand and explain the photoelectric effect. Then if the electromagnetic wave is a photon, a particle, then they also carry a mass and momentum, and this is a formula for that. And we can use this picture to study the so-called Compton effect. And why the Compton effect is important is that now when the electron is excited in the atoms, they will jump back forth in the energy levels, so they will emit the photon. And this is the difference of the frequency of the photon emitted. And this is a relation between that. And finally, is one of the most important assumption and hypothesis in the quantum physics is that if the wave have the particle property, then if it is a particle, then they also have the wave property. So the wavelength of a particle is defined in terms of this. It is the h divided by the momentum carried by the particles. So now we reach to a very new scenario, is that wave and particle dualities.